Okay, we've worked out the lattice enthalpy of sodium chloride. That was the simplest one. And then we did the magnesium chloride, which was a bit trickier because you've got to think about the second ionization energy of magnesium and also the formulas of MgCl2. So you had to multiply a couple of the chlorine values by 2. Now we're going to do probably one of the more difficult ones, most difficult one really. And we're going to do it for magnesium oxide. So let's think of the data we're going to need there. Well, we're going to need delta HF for magnesium oxide, which is endothermic. Sorry, it's not endothermic, it's exothermic, isn't it? So the exothermic. We're going to need delta H at for magnesium. So that's the enthalpy change when you form 1 mole of gaseous magnesium atoms for the elements in the standard state. That's definitely endo. We need to know the delta H atomization for oxygen. So and that's endo, because you have to break the bond between the double bond between 2 oxygen atoms. We also need to know the first ionization energy of magnesium and the second ionization energy of magnesium. Then this is where it gets a bit more tricky because we need to know, they're both endo. We need to know the first, because we're talking about the oxide ion, the O2 minus ion. It's got 2 electrons, isn't it? So we need to know the first electron affinity. Of oxygen, which is when you go from O gas plus an electron to O minus. And you also need to know the second electron affinity, which is when you go from O minus, the single charge oxide ion, stick another electron onto that, and you go to O2 minus. Now, this is where it gets tricky, because this one is exothermic, and that has a value of minus 141 kilojoules per mole. Whereas this second one is endothermic, and that is, doing blue, that is plus 793 kilojoules per mole, which is going to make our Born-Haber cycle look a little bit funny, because it's going to go down here, and then it's going to go sort of back up again. So it's going to look something like this. Right, here's our, I'll just sketch it here. So we're going to start off with our magnesium and oxygen, and it's going to go up and up and up and up and up. All these, okay. And then we're going to get the first electron affinity, okay, and it's going to go down. So that's going to be, and then they're going to get the second electron affinity, it's going to go back up again. And that's going to be our Mg2 plus and our O2 minus at the top. And there's going to be our magnesium oxide there. So it's going to have this, and then this is going to be the lattice enthalpy of formation, isn't it? That bit there. So we're going to go up, up, up here, down for the first electron affinity, and then back up again for the second electron affinity. So when we come to working it out, we're not going to worry about signs as usual. What we're going to do is we're going to add up all that lot there in red, and then we're going to add on that bit in red there. But then I'm going to have to take away this bit in blue, and that should give us the green, the lattice enthalpy of formation here. Okay, so that's a little preview of what we're going to do, and I might have to scroll up and down the screen a little bit because it's a bit awkward, but yeah, don't forget that. Okay, let's try this one then. Right, at the bottom of the screen, I'm going to rub some of this off, I think. Okay, so here is our energy line. Start off with the elements in the standard states, as always. So I'm going to start off fairly near the bottom here. So we have Mg solid plus a half O2 gas. Right, we're going to form that into magnesium oxide, aren't we? So that's going to go, that's delta HF, that value there, isn't it? And that's going to be MgO solid delta HF. Right, so we need to turn the magnesium we need to go from magnesium solid eventually into magnesium 2+ at the top, don't we? Gas. So the first thing we do is atomize the magnesium. So here we have Mg gas plus a half O2. We've done nothing to the oxygen. That's delta H at. Then we are going to have to do the first ionization energy of magnesium. So we're going to turn it to an Mg2+ ion, 1+ ion, sorry. Gas. Nothing's happened to the oxygen. So that's going to be the first ionization energy. And then we're going to turn it into Mg2+ ion, so that should be bigger, shouldn't it? Mg2+ gas and O2 gas. That's the second ionization energy. So we're glad to have left some room. So now we're going to do something to the oxygen. We're going to have to turn the oxygen O2, and we're going to turn it eventually into the oxide ion. First step is to atomize the oxygen. So that's Mg2+ and O gas. I should put a half there, sorry. Half, and I should have a half there as well. That's delta H at for oxygen, forming 1 mole of gaseous atoms for oxygen, so it's just 1 times delta H at. Now we come to the electron affinities, okay? This bit here where it gets a bit tricky. Now the first one is endothermic. It was a value of -4.1, so we're going to go down a little bit. So here we're going to have Mg2+ gas plus a singly charged oxide ion. And that's going to be the first electron affinity. And then, and that's why I'm glad I've left that there, so rub it out, got some room. I've got to go up because the second one is endothermic, so that's going to go up. And here we have got Mg2+ gas, that's what we've been aiming for, and O2- gas. So now what's it going to be is we're going to have the lattice enthalpy is all this big, it's going to be really long. This is lattice enthalpy of formation all the way down from there down to there. Okay, so let's put some numbers in and work out the values for this one then. Okay, so right. So here we go. We have got, right, delta HF of magnesium is -602. I'm going to rub out this blue line, give myself more room. -602. Delta H out, magnesium, 148, positive. First ionization energy is 738. Second one is bigger, 1451. Atomization of oxygen now, that has a value of 298. The first positive, the first electron affinity is -141. And the second one is plus 793. Right, so our first job is to add up all this, and let's do it in blue, shall we? Awesome. Yeah, add up all this blue stuff here. So how high is it from the bottom up to that first shelf thing? Yeah. So if I do all that, I can shrink this. Okay, that's better. Right, so I'm going to have 602. Again, ignore the negative sign because we're going up. Plus 148, plus 738, plus 1451, plus 298. That's 32. All of that there is 3237 kilojoules. And then we're going to have to go down here, and I'll do that in green or something. Yeah, that bit there, that's going down. The first one is that's -141. And then we're going to have to go back up again by this stuff, which I'll do in red, 793. So if I want to work out the lattice enthalpy going from there to there, what I need to do is, it's 3237, and then I'm going to go down, so it's -141, and then I'm going to go back up again, so it's plus 793. Put all that in, you get a whopping 3889 kilojoules. It's very big lattice enthalpy. And is it negative or positive? Well, it's formation, and the arrow's going down, so it's negative. So that is our answer. And of course, it's such a big value because the magnesium is 2+, double charged. The oxide ion is 2 charged. Okay, force between the ions, charge on one positive ion divided by the times by the charge on the negative ion, divided by the separation of the ion squared. Well, the magnesium ion is pretty small and the oxide ion is pretty small, so this R value is small. So you get a very strong force between them. You need a lot of energy to break up the lattice. So that means you get a lot of energy when you form the lattice. So we get a big negative value for the formation of magnesium oxide there. Right, let's leave that there.